Welcome to Physics with Vinay.
Hi, I'm Vinay and I'm back for season 2. This is the 6th episode of the Rare series, and in this episode, I'm going to bring you a very similar question or a similar concept to what I did in the previous episode in the same Rare series. If you watched my previous episode, I calculated the force on an electric dipole using two methods, and most of you were able to figure out which method is correct. I was very happy to see that. I'm going to do a very similar thing in the magnetic moment case. Here you might have to be a little more careful, so let's take a look. So I have magnetic field lines which are circular in direction, and their magnitude varies as the distance is proportional to the distance is equal to AR. A is a positive constant, and the distance is measured from the origin. So the question is saying that the magnetic moment is placed at r comma 0. So it's placed on the x-axis, and the magnetic moment is given by m I cap. So find the force on the dipole, the magnetic dipole. So I'm going to do it using two methods, and once again I want you to figure out which method is correct and why. So let's take a look. So let's look at the first method. So before I do the calculation, I just want to quickly go over what will happen in the case of an electric dipole. In the case of an electric dipole, we had two methods. In method 1, we wrote down the potential energy of the dipole as minus P dot E, and then we calculate the x component of the force as minus del U by del x, which will basically be the partial derivative of P dot E with respect to x. And similarly, you can do it for the y component and the z component. So this is one method, and we saw in the previous episode that this is only valid if the electric field is conservative. Only then you can define a potential energy. And method 2 was to treat the dipole as 2-point charges and then calculate the individual force on that and then take the resultant. So in that case, the force came out to be P times dE by dl, where P here is the magnitude of the dipole moment and dE is the electric field change from the negative to the positive charge of the dipole, and dl is the length of the dipole. So these were the two methods that I showed in the previous episode for the electric dipole case. And what I'm going to do is the very similar thing for the magnetic moment case. So method 1, I'm going to write that the force x component of the force is going to be the derivative of, so instead of P dot T, I'm going to use m dot B. So this is one method, and similarly for the y and the z component. So my magnetic field lines are in a circular manner. So let's say at an angle theta, the magnetic field is in this manner. So this angle is theta. So magnetic field basically makes an angle theta with the y-axis. I can write it as, so the magnitude was AR, so I can write it as AR minus AR sine theta I cap plus AR cos theta j cap. Now what is R sine theta? See, R is the radius of this magnetic field line. So R cos theta is nothing but x and R sine theta is y. This will come out to be, if I take A as common, minus y cap plus x j cap. Now if I calculate m dot b, what is m dot b? M was m I cap. So m dot b would simply be minus m a y. So the x component of force will be 0, there is no x term. So the y component of the force would be the partial derivative of minus m a y, and that will come out to be minus m a. So therefore my force would be minus m a j cap. Alright, so this is the force using the first method. Now let's look at the second method. So in method 2, like we had in the electric dipole case, we had P dE by dl. I can write force as m dB by dl. So the magnetic moment is placed on the x-axis. Magnetic moment is on the x-axis. So therefore on the x-axis, my magnetic field lines, if I just look at the magnetic field direction, they are all along the y-axis. And the magnitude will be proportional to the distance from the origin, which is basically x, as far as the points on the x-axis are concerned. So can I write magnetic field? I am only writing on the x-axis. Magnetic field would be AX j cap. Alright, and dl was along the dipole. So the dl will basically be equal to dx because the magnetic moment is along the dipole. So therefore the force would be m times the derivative of AX j cap. So this will be ma j cap. So if I look at the first method, my answer was minus ma j cap. So the force is in the negative j direction. And the second method, the force is in the positive j direction. So I want you to once again post your comments in the comment section and let me know which method you think is correct and why. That's it for today. See you at the top. Good night.